Hello and welcome to chapter 15. We're in the middle of the chapter, about on page 5 of your notes, and I'm going to do a little bit of review in this video. This is an example of a titration curve. We've talked about it before, but this is for a strong acid, strong base reaction. I know that because my equivalence point's at 7 right here. Remember, equivalence point's halfway up this line. Some other important things. My starting pH is pretty low. That tells me it's a strong acid. This area is my buffering zone, or where my pKa would be ideal. So the ideal pH of this acid, or the Ka, would be somewhere right around here. That's helpful on a question on your AP exam from today. And remember, when something's at its equivalence point, that means it has equal moles of acid and base. Okay, another example, you have those in your notes. Now, we talked about a strong acid, strong base titration. We already did this calculation together, but just as a reminder, we tend to do these in millimoles. What that means is we don't convert out of milliliters to make the math a little easier. And to do that, we do our molarity times our volume. So we always have this net ionic equation that's just making water when it's a strong acid, strong base. Okay. So first up, when we see a question, we have to do stoichiometry. And what we're going to do is think about each step. So this question asks, what happened initially first? What do strong acids and bases do in water? They completely disassociate. So it's super easy to calculate our pH. All we really have to do is say it breaks up completely. So my H plus is going to be equal to my big M, and I'm going to plug that into the negative log and get my pH of 0.699. Next, it wants to know after 20 mils. So after we add 20 mils here, we need to do a little stoichiometry. And what I'm going to do is put my equation that we talked about and take my milliliters times my molarity to get my millimoles. H will stay the same throughout. Nothing changes the concentration of H plus unless you were to add another acid. Why would we do that in an acid-base reaction? So that's never going to change. It's going to be 10 the whole time. But for my OH negative over here, I have to use my 20 milliliters and my 0.1 molar in order to figure out my millimoles. So essentially all I did was put these on the same playing field. I'm comparing moles to moles. You really can't compare molarities like you can compare moles. Then I essentially did an icebox. Before my reaction, I have the 10 and the 2, and how much it's going to react is whichever one I have the least of will go to completion. So I have 2 moles of my OH negative, came from my NaOH. I'm going to subtract that from each side. And in this case, my limiting reactant was my base. So in other words, it's still really acidic. So this 8 moles is what's really important to me now. Now I'm going to plug that in to figure out my concentration. And my concentration is the same as molarity. So I'm going to put my moles over my liters. But remember, I'm doing millimoles, so I can keep these in milliliters. 50 was the amount of HNO3. And 20 was the amount of my NaOH. In order to give me a total of 70, divide that, and I get 0.11 molar. What do I do now to find the pH? Just take the negative log, and I'll get 0.942. Didn't change very much. There was a question similar to this on the exam as well that said we added a strong acid and a strong base or something like that, and how did the pH change? And it really didn't change much when we added only a little bit. Now I've got 100 milliliters. After 100 milliliters, I'm going to do the same exact thing. My H will be the same. My OH is going to be 100 mils times my molarity. And look, oh man, they're even. If I were to subtract it, these would essentially both be my limiting reactant. That's when we say it's at its equivalence point. The same amount of moles of hydroxide as hydrogen ions. So it's the equivalence point. Everything is equivalent. What are my major species here? Well, I have my sodium, which, we kind of ignore, and my NO3 minus, which we kind of ignore, and my water as well. But what it's saying is that, you know, a neutralization reaction forms a salt and water. So I essentially have salt water that's at a pH of 7. They don't have any acid-base properties. So every time it's a strong acid, strong base, we get out a pH of 7 at our equivalence point. But we're not done. We also have our 150 mils. So now on our curve, we've gone past that middle point and we're up here at the top. Do the same exact thing, but the only thing that changes here is now my limiting reactant is my H+. It's all been used up. I'm going to plug it in here, subtract my 10, and now I have an excess of base. So this excess of base will swing my pH over so that my pH is now on the basic side. Hopefully you know by now where I got these numbers from, and all I'm going to do is plug those in like I did before, but here's the difference that you have to notice. Now I'm talking about OH concentration. That's why it's so important to keep track. And I have my 5 moles on top over my total volume. What's this going to give me? Well, that's going to give me, if I take the negative log, my POH. That's not what the question asked. It asked for the pH. So I need to take this 1.6 and subtract it from 14 in order to get my pH of 12. Now I could construct one of those graphs if I needed to, and that could be something you'd see in a free response section. Okay, so I want you to try this one. Follow it step by step through those last couple slides just like I did, and you can always rewind this and go back, and we will go over this one Monday in class, so please try this one.
Hydrochloric acid is a strong acid that completely dissociates to form H+ and chloride ion in solution. The H+ ion is rapidly solvated by water, forming the hydronium ion as shown. The hydronium ion reacts with the hydroxide ion from the dissociated strong-based sodium hydroxide to form water. In this neutralization reaction, sodium and chloride are spectator ions that do not participate in the reaction.
Notice that he said hydronium. I want to fast forward this here.
Hydrochloric acid.
Yeah. So notice out here, he said hydronium, because every time we write H3O+, this is what it looks like. It actually has 3 hydrogens on it. And what are these guys floating around? The green and the white are my leftover salt particles. So really it's about how many of these extra hydrated waters I have floating around. I think we realize that. Okay, so we talked about strong acid, strong base, but what if it's a weak acid, strong base titration? Well, just think about pH here. If we have a weak acid, is it going to be very effective with a strong base? Not really. So I need to consider the ratios and follow the same exact process as before. So essentially what we do is the first stoichiometry part, and we think about how the hydroxide ion and the weak acid are going to react together. Okay, and we'll walk through one. And then we do our same equilibrium process to figure out our pH. Alright, so here's our example. 50 mils of a 0.1 molar acetic acid is titrated with 0.1 molar sodium hydroxide. You should read that. They're not going to say, hey, look, weak acid, strong base. You have to recognize those, right? So weak acid, strong base. Calculate the pH of the initial concentration of acetic acid, and after 25, 50, and 60 milliliters of our NaOH has been added. And they gave us our Ka here. Now this isn't as easy as a strong acid because remember, weak acids only dissociate 1%. So before it's added, how am I going to calculate it? Well, I have to do an icebox. I have to figure out my equilibrium. So I know my reaction here. My acetic acid is going to break up and release those hydrogen ions. And I know my initial concentration here was my 0.1 molar. And I had 0 of the others. Which way is it going to shift? To the right. So I'm going to use my 5% rule. Say, hey, it's going to be less than 5%. It's a weak acid. Plug it in using my Ka and calculate for X. Then what do? Natural log, get my pH. So you should recall all this from last chapter. You just have to now recognize strong base, strong acid titration versus weak acid, strong base. So when we have a weak acid, follow this same process we have been before. It just kind of adds an extra step. There's my initial pH. Now I add 25 milliliters, and let's see what happens. Well, my reaction changed a little. Now I'm taking my acetic acid and I'm putting my hydroxide on the left side. And what I get out is water and some of my acetate ion on the other side. So I'm just going to do my conversions. It said I added 50 mils initially of this 0.1 molar. So I got this from the initial problem, which I'm sorry it didn't transfer over to this slide. And this is where my 25 milliliters and 1 molar are going to come in. I don't even have to worry about the other side yet at this moment. So then I'm going to go down into my box here, and I'm ignoring my H2O because it's a liquid and just plugging in what I know. Well, I know it hasn't produced any acetates yet. So the acetate's going to be produced when this OH steals away an H here. So I'm plugging in my numbers. That's easy because it tells me where it's going to shift to the right, but I have to know how much it's going to shift, and that's where this number being less comes in. So I need to subtract, just like you would subtract x, add x. Instead, it's like I know my x. My x is my OH negative. So plug those in and get out your numbers. Whatever comes out to 0 is my limiting reactant. And now I need to take these numbers and use them in my ice box. So the reason it works this way, which I'm not sure if I clarified before, is I want to know the pH. What is the pH? That's the amount of hydrogens in solution. How can I calculate that? Well, I have to use my HC2H3O2, my acetic acid. I have to say, hey, what's this guy actually going to do when it reaches equilibrium? He's going to break up into its two ions. But I already have this other ion here. And what this essentially acts as is a common ion. Okay, just like our common ion situation. So think about it that way when we're thinking about acids and bases. What I did here was the same thing as before, where I'm converting back from moles to molarity. And I'm taking my millimoles on top, because I'm caring about this guy right now, over my total volume to get a molarity of 0.033 molar. Then I have to do the same exact thing for this guy to get out a molarity. A good way to remember this step is that, you know, this is like our bra box we joked about. When we're talking about stoichiometry, it can be millimoles. But when we're talking about an ice box and we're talking about pH, it has to be molar. So convert it to molarity before you plug it back in. So then I'm going to take all these numbers and put them in an ice box. Oh, I could have done an ice box. Sorry, I totally forgot. I put the shortcut in here. So instead of the ice box, I did the Henderson-Hasselbalch equation here. And I did my negative log of my Ka plus my log of my conjugate base, or the leftovers of my acid, this guy, over my acid, this guy, to get out a pH of 4.74. Look what a huge, that was a pretty big change in pH compared to the last example problem we did. So on the flip side, you could have done an ice box and you should have got to the same pH here. All right. So that was after 25. Now we're on to 50. After 50 mils of 0.1 molar is added, we now have the same exact reaction as before because it was at equilibrium and we just took it out of equilibrium by adding 25 more mils. So I'm following the same process. My HC2H3O2 never changed, same amount I initially put in. Now this is 50 mils. I'm ignoring the stuff on the right for now. And I'm going to plug it into my bra, or whatever you want to call it. And it's going to shift to the right. Well, what am I going to subtract here? Either one. That automatically tells me I just reached equilibrium on the left side there. And on the right, I'm left with an excess of my C2H3O2 ion. Now, I'm at my equivalence point because my moles of acetic acid and hydroxide are even. So I'm considering my major species and seeing if they have any of these properties we talked about. And technically the acetate does because it's a conjugate base. And because of that, our pH shifts just a little bit from 7. So it won't be 7 like the strong acid, strong base reaction was. Okay, we will be back on the rest of this in the next video. See you soon.